get started. I mean, yeah, by the way, we uploaded the homework 1 to the EE class. If you have not checked out the homework 1, please, I mean, do it like as soon as possible. I think the due date is next week. Is that right? Yeah. Okay. And so I believe like that's for like the first 3 lectures. Okay. So this one is not covered in the homework 1, by the way. Okay. So you should have enough material. Okay. I mean for homework 1. Okay. And so this lecture 4 is for the quicksort. Okay, the quicksort is also a divide and conquer algorithm. Okay, so remember, like we talked about merge sort, right? Merge sort is a divide and conquer algorithm for sure, and we talk about merge sort like I think in the first lecture, right? And but the idea, behind the merge sort and quicksort are very, very different. Okay, even though they are both divide and conquer algorithms. Okay, so first, okay, the quicksort. Okay, this algorithm is proposed by C.A.R. Hoare in 1962. You need to understand, 1962 is already like a very late time to propose a sorting algorithm. Okay, after all, like most of the sorting algorithms were proposed like much earlier than that. Okay, and also C.A.R. Hoare is a very, very famous algorithm researcher. Okay, you can check out like his like Wikipedia. Okay, you will understand like he did a lot of contributions in algorithm like research. Okay, so this is obviously is a divide and conquer algorithm, as I already mentioned to you, and it sorts the numbers in place. So what is in place? In place means like you don't need additional space to sort these numbers. Okay, so we know like insertion sort also has similar nature like that, right? Because insertion sort, we just like every time we try to put a number at the right place, right? So we really do not need like one additional copy. We may need like just like a buffer to store like just 1 or 2 temporary like index or numbers. That's it. Okay, for insertion sort. Same thing can be said for quicksort. Okay, quicksort has that good property because like after all like I mean if you need like additional space to store the whole thing, okay, it is like remember like we talk about like a complexity. Complexity can be discussed like in running time. It can also be discussed, I mean, for like a storage consumption. Okay, so for example, merge sort is not an in-place sorting algorithm because like a merge sort, we require one complete additional copy at a different location. It's just like remember like you have 2. I keep telling you guys like merge sort is just like you have 2 sorted deck of cards, right? So those 2 sorted deck of cards, of course, they occupy spaces, right? Okay, but when you put them together, when you put these 2 sorted cards together into one sorted array, I mean you need additional space to hold the result, right? 就是 merge sort 你是2个已经排好序的2堆，你把它合成一堆，排好序就把它合成排好序的一堆嘛。那你那2堆放在那边需要占空间，对不对？那你再把它排成一堆 就是把它就那个合成一堆排好序的，也需要占空间，对，所以你需要一个 additional space 去store 这个所有的东西，所以 so that's why merge sort is not like a quick sort or insertion sort, like it consumes like a much more storage space. Okay, and quick sort is very practical. What do I mean by very practical? I mean like it is, you know, you can tell by the name of this sorting algorithm. It's quick, right? It's quick. Okay, but of course, like remember, like what when we talk about like you know, when it comes to sorting, okay, it depends on how many elements are you talking about. If you every time when you do a sorting, you have only like a couple of elements, maybe like less than 10, then insertion sort is actually the quickest. Okay, I mean, even though it is not the advanced sorting algorithm, but it really like it's a very cheap algorithm when the number of elements is low. Okay, but okay, when it comes to like you know, relatively larger size, okay, quick sort is usually the best. Usually the best. I mean, so that's why it is practical. But you need to tune it. Okay, there are several ways you can tune the quick sort. Like randomize the quick sort is one way to tune it. I mean, we will talk about that. Okay, in this lecture, but probably not today. But yeah, that's our plan. Okay. So, as I said, quick sort is a divide and conquer algorithm. Okay, so if you remember, the merge sort, okay, the division happens so easily, right? You just find the middle element, you break it into half, and then you keep doing that, and then you know, you just merge them. Like I mean, when you break, I mean the arrays. I mean, you know, you keep breaking the array. Eventually, you have only like one subarray. I mean, one element in the subarray, like it is considered sorted, and then you merge them, okay, to form a sorted array, and you know, eventually you form like a complete sorted array. Like that's the concept of merge sort. And as you can tell, like the merge sort, like the most of the work happen in the merge part. Okay, so it's not. Or, yeah, it's really like the merge part that takes most time. Okay, that's like the nature of a divide and conquer. I mean, nature of the merge sort. But for quick sort, okay, the most effort actually happens in the divide part. In the divide part. Okay, so first, okay, let me explain what we intend to do. Okay, what we intend to achieve. What we intend to achieve in the divide. Okay, in the divide part of the quick sort. Okay, first, we would like to partition the array into two subarrays. Okay, around a pivot. Okay, this pivot we call it x. This pivot x. Okay, so x is a spatial element. Okay, we call it pivot. So that, okay, the elements in the left-hand side, okay, are all smaller or equal to x. And the element on the right-hand side are all larger or equal to x. Okay? So x sit in between. Okay? So the most of the work, as I say, happened in the division. And this x, there are a few implications here. First, if this is the case, X is already at the right place, right? We don't need to move X around anymore because, well, if all the elements, on the left hand side are small or equal to X, all the elements on the right hand side are greater or equal to X, well, obviously X is at its rightful place, right? 它就是已经被排在对的地方了，对不对 ？Okay. So this is the first implication. The second implication is that, okay, because X, this pivot, okay, is chosen, okay, when it was chosen at the beginning, we do not know, its ranking among elements. 就是它到底有在这个 element 之间，它到底是排到第几个，我们不知道。So after we achieve this configuration, the left subarray and the right subarray, their size, okay, are not, most of the case, are not necessarily equal. Okay, 记不记得在 merge sort， 我们每次 把它切开来的时候，都从中间切，对不对？对，所以我们保证这个 merge sort， 它切，都是左右的 subarray 都是一样大的。OK， 但是在 quick sort， 因为我们要保证 ，because we want to guarantee such a configuration, so this left subarray and right subarray could be very different in size. Okay, of course it depends on how you pick that pivot. Okay, so that's the divide. And the conquer, we just recursively sort two subarray, recursively. Okay, and the combination takes no effort. So you can see that, the quick sort is almost like its design principle is almost opposite to the merge sort. The merge sort, the divide doesn't take much effort. Conquer, it's the same. We just do it recursively. Combine takes the most effort. But the quick sort is the opposite. Okay? And the key point is the linear time partitioning subroutine. So how do we, divide? How do we achieve this configuration? Okay, when you are given an unsorted array, that's the key point. Okay. And also, I need to remind you, okay, there are more than one version of quicksort. Okay, 就是这个 quicksort 有不止一种版本. And in fact, at the time when I learned the quicksort the first time, okay, 我学 quicksort 的时候，那是我大4的时候吧，我第一次学 quicksort. Okay. 因为我是数学系嘛，所以 because my major was not in computer science, so I studied these things by myself. Okay, so the first time I learned the quicksort, I learned a different version. Okay, to be very honest with you. Okay, but the version that I'm teaching you, okay, is the most popular one. Okay, the most popular one. Okay, if we have time, I would. I hopefully I can talk a little bit about the version that I learned. Okay, probably not today, maybe next time. Okay, so the idea is this. Okay, because this partition is going to be called many times. Okay, so we are going to be able to partition a subarray. So that's why. Okay. This array A, we are doing P and Q. Okay, P, Q just stands for the range of this subarray. Okay, the range of this subarray. Okay, and okay, we assume the first element the first element, AP, okay, so P and Q, okay, they are here. So P is the first element, the index of the first element. Q is the index of the last element in this subarray. Okay, so obviously, P is smaller or equal to Q, obviously. So at the beginning, we assign the first element, okay, AP, to be the pivot, okay? And then, okay, the idea is like this. Okay? During the whole process, okay, we have two index, I and J. Okay, the elements, okay, from index P plus 1 to I, from P plus 1 to I, holds the elements that are smaller or equal to X. Okay? And the elements, okay, in between index I plus 1 to, J minus 1, I guess, okay, to J minus 1, holds the elements that are greater or equal to X. OK， 所以这一块包含的是比 x 小的元素，我就不要讲说什么小于等于，就是比 x 小的，等于是 given 的。那这一块是包含比 x 大的元素啊。Beyond this point, okay, is the part that we have not finished. We are doing this. Okay, this is like during the process. What it looks like. So you could imagine, because at the beginning, we don't have this part, right? We don't have this part, right? 在开始的时候，我们根本这两块都没有嘛，我们没有保证任何一个 element， 就我们只知道第一个 element 是 pivot， 那其他的我们都还没有 process， 就等于说所有的都是这个。对不对？这有问题吗？没有问题吧 ？OK， 所以这两个部分都没有 ，because these two parts, are still, empty. So you can see that, okay. Start from P. So as I say, like this section, is from P plus 1 to I, right? So because I start from P, so it pretty much indicate this part is empty initially, right? And then J start from P plus 1 to Q. So it's really, initially it starts from this index, okay, to Q, but the Q is, what is Q? Okay. This is the for loop. I'm sorry. So J is from P plus 1 to Q. So it's P plus 1. Okay, but remember J stands for like the first index that have not been processed, right? So when we say J start from P plus 1, that means like starting from this place. Nothing has been processed. 在开始的时候，从这个 element， 从第一个 element， 就是在 pivot 之后的第一个 element， 所有都没有被 process， 也就是这边没有东西啦，对不对？大家可以接受吧 ？OK， You guys are still with me, right? Okay, so then do if AJ smaller or equal to X. OK， 如果我们现在看到这个。这边第一个没有 process 的，它是小于等于 x 的，那我们是不是可以 grow 这个 section？ We can grow this section, right? Okay, because we found that this element is smaller than x. So what happens is that we increase the index of I. Okay. And then exchange AI and AJ, what should I say? Like, let me see. AJ 这边好像有点错误，看一下 J。Oh, okay, okay. So let me use this one as a, because this is more general case. Okay, if AJ is more or equal to X， 在这边嘛，那 I 是不是在这边？对不对？那我们第一个把 I 长到这边，我们要留一个空间。We need to reserve a space for this smaller element. So then we exchange these two, so that we grow one element here to make this part like containing the element smaller than x， 对不对？然后把这个原来是比 x 大的嘛，那我们就把它放到这边来，那这一块还是比 x 大的，所以我们需要做一个这个 exchange。那 we keep doing that until J grows to Q, right? We finish the whole array. 那整个做完了以后，这一块是小的，那这一块是大的，然后我们已经没有这一块了 ，we are out of this part， 对不对？所以呢 ，we exchange AP and AI， 我们把这个跟这个交换，这两个交换，那这样子的话，在 x 之前的都是紫色的，都是比它小的，在 x 之后都是比它大的，因为这一块已经没有了嘛，对不对？这样了解吗？这样了解啊？这边有一个那个，就是说我们在这边走的时候，我刚刚不是讲 ，I was talking about okay when AJ is smaller than X, we do something, right? But how about if AJ is greater than X? Nothing needs to be done. OK， 因为我们就把这个就是这个粉红色的往这边长就对了嘛，对不对？就是比这个 X 大的，因为如果这边是比 X 大的，我们就继续长就好了。好 ，Let's have a look at the example. So, this is like an array, a random array. Okay, we start. I start from here. J start from here. Okay, and the pivot obviously is 6, right? As I said. Okay, and everything, every element after the 6, they are not processed yet. So, okay, initially, okay, because 10 is greater than 6, so nothing needs to be done. We just simply move J to the next index. And again, 13 is greater than 6, so we move J further to here. And then, because 5 is smaller than 6, so what happens is that we exchange 5 with we move the I one position to the right, okay, to point to 10. And then we do exchange between 5 and the 10. So what happens is like this here. We move I to here and then do exchange. So I is pointing to here, and J is here. I'm pointing to 10. So again, J move to next position. Okay, A is greater than 6, greater than pivot, so nothing need to be done. And then the next position is 3. Okay, 3 is smaller than 6, so what happens is that we move I one position to the right and do exchange between 13 and the 3. So that's the the result. 13 is placed here, 3 is here. Okay, and then okay, obviously like the next element. Wait a moment. We need to exchange. So we exchange 3 with 13, so it becomes here. And then the next element is 2. 2 is smaller than 6. Again, we need to move I one position to the right, and then j here pointing here, like do an exchange. So it become like we exchange these 2 and the 10. Okay, and the next one is 11. So we are done. Okay, 11 is greater than 6, so nothing need to be done. So at the end, we exchange 6 with 2. Okay, to make 6, at the right place. To make 6 at the right place. So that is how quicksort gets the job done. I mean, when it does the partition, or when it does the divide. Okay, so you can see that at the end, 6 is at the right place, and then we need to continue working on the left side and the right side recursively. Okay? So that's the idea of the quicksort. Okay, the idea of the idea of the partition or divide. Okay? And then once you understand this partition or this divide, okay, the quicksort just looks like that. See? We start, okay, quicksort A, P, R. Okay? If P is smaller than R, okay, it means like this is still represent a subarray. Okay, it still carries some elements in here. Then, the first element, we are going to, do the partitioning. Okay, A, P, R. We call the partition A, P, R. And we assign Q the result, the returned value to Q. What is the return value, by the way? I forgot to mention about that here. Return I, we are going to return. Remember, at the end, we exchange P with I, right? So we will return the index of the pivot. We are going to return the index of the pivot. So in other words, in this case, we are going to return the index here. Okay, we are done with the partition, and we return the index I. Okay, so because you are done with this partition and you return the index of the pivot, so you are going to call quicksort recursively on the first subarray. So it's A from P to Q minus 1, and the second subarray is array A from Q plus 1 to R. Okay, so that's it. So initial call, you just call quicksort A1n because you original array starts from index 1, and the last index is n. So that's it. So it is very, very elegant sorting algorithm. Once you understand the how the partition is done. Okay, so I think I will stop here today. Next week we are going to discuss the complexity of the quicksort, and also we are going to, as I say, I'm going to try to tell you another version of the quicksort, and also we are going to dive into the randomized version of the quicksort. Okay, and how the randomized algorithm help to reduce the complexity of the quicksort. Okay? Yeah, that's it for today.